points that the vast majority of the machine learning models, so think about supervised learning, unsupervised learning, they're not causal in nature. What the explanations are telling you is that there is some target variable and there are some correlations. You say that, oh, there is some causality, but that's not what the model itself is saying. Okay, so which brings us to healthcare AI. And okay, so the question is, well, why do we need explainability in healthcare AI? So one, it is either everywhere or it is going to be everywhere. And a related question that we can ask is, why is it that the discussions around it are happening in the present? So the reason for that is that A, wide deployment, availability of large amounts of data, and secondly, also to look at just the interest in AI in general. So this is a good visualization of just the amount of publication in AI research, and it has skyrocketed around, I would say, almost 10 years ago or so. Okay, so that's explainability in general. So now, in the context of healthcare, so why do we need explainability? So these are the various scenarios where that's applicable. So when you require fairness, when the consequences are far-reaching, cost of mistake is high, so you do not want to misclassify something that should be classified. In scenarios which you're encountering a domain which is not very well understood. So you can use explanations to actually form hypotheses, even design studies. And of course, there are regulations, so we talked about GDPR, also when you have models, which may be better than humans, but still the explanations or the prediction, level of prediction is still not that great. Or maybe the model works better on parts of the data where humans are not very good, and vice versa. So you need explanations. Okay. And then also we talked about scenarios where the record of applicability of AI has been less than stellar. So, for example, the fiascos associated with some of the examples shown here, especially IBM Watson. To reiterate an example that we talked about previously, so IBM Watson was recommending basically certain actions, if they would have been taken, have actually been detrimental to the patient. And then there are a couple of other examples. So this is basically the asthma and pneumonia example that we went over yesterday. So for the sake of clarity, I will describe this again. Okay. So the scenario is basically that if you have a black box model which does well in a particular setting, it could be the case that it's using certain domain knowledge in your data. We may end up in a situation where actions taken based on that recommendation would lead to a negative consequence. And then here's another example of adversarial learning where we have models which can basically look at different types of data sets. And again, it's easy to fool these models by injecting just very small amount of noise. So that said, so in both of these cases, if there was some explanation associated with why the prediction is being made, presumably these problems could be detected early on. So another thing that I should mention is that, so when we talk about AI, so AI is actually an extremely wide field. It's been around at least since the 1950s, and some of these antecedents go even back. So when we talk about explainability, we can talk about explainability in a large number of subfields within AI. So our focus for today is going to be mainly around supervised learning, and the reason for that is that it is very prominent in applications of supervised learning, and especially when it comes to healthcare, mainly supervised learning related problems, you can say that can account for upwards of 80% of problems that we encounter. Okay. And then this is okay. So this is basically the life cycle view of AI or machine learning in healthcare that we talked about earlier. So we are actually going to use this as a running example over the course of time to explain different or elaborate different aspects of explainability and at what points in time do people encounter them. So our running example is going to be a person, in this case it's a data scientist who is going through the healthcare system and what kind of problems that he or she can encounter. And how do we map those back to real world problems as well as machine learning problems? Okay. And then to reiterate an extremely important point, that when we talk about, again, machine learning models, AI models, they are a very small part of the infrastructure that is required to operationalize AI. So that is over here. In order to actually run an AI ML system in the real world, you actually do need support technology. All right. So let's talk about because we're talking about explainability model, you need the following three elements. 11 on even before talking about explainability. So syntactic correctness. So for example, if you have data coming, so think about a data pipeline, data coming from multiple sources, so there should be correctness with respect to the syntax. So it's like something like, say, encoding for gender, say male, could be MALE, it could be capital M, small m, or even the number 1 or 5 or whatever. So morphological correctness, so the data is the data with respect to a particular range of values. So say for blood pressure, say a value of 500, that does not really make sense. Semantic correctness. So if the data is coming from, especially from multiple sources, it may be encoding for different things. So for example, let's talk about what constitutes normal blood pressure. So the way that is encoded normal versus abnormal for, say, general population versus pediatric or for children is very different because definition of what constitutes normal would be different. So again, that's an extra area of check that is required. All right. Okay. So let's actually do a quick audience poll. Okay. So question 3. So explanations are needed in healthcare to foster trust, reduce the risk of and fall, decision-making, compliance, all of the above. So A, B.
All.
As I said, these are easy. Just to ensure that everybody's awake. Okay, so now we will talk about what are known as the pillars of explainability in healthcare. So it's basically within the context of healthcare, if we want to create a system which is explainable, what are the different aspects, what are the different properties that an explainable system should have? So let's look at these. So transparency, domain sense, consistency, parsimony, generalizability, performance, fidelity. So let's actually discuss each of these one by one. you. All right, thank you. All right, so let's start with transparency. Okay. Okay, so now so here we'll explain each of these different pillars from the perspective of, say, there's a researcher, and then basically she's going through, say, a particular use case within a particular hospital in the emergency department, and so how she navigates. So the first one is transparency. So transparency is basically the ability of the machine learning algorithm or model and the features to be understandable by the end user. So what does that mean?
So the end user is a doctor or is
it a member? It's a member. It's a patient. All right. Okay. So this hypothetical person in our case is Catherine, and so she has built a model or analyzing a model to predict likelihood of admission to the hospital. So this is 0.62. So the physician looks at, say, the stats associated with that patient. And so the physician, when he looks at the model, so it makes sense, but then the model is a deep learning model. He cannot understand what's going on. So presumably there's a dashboard like this. Okay, so when we talk about transparency, we have to define transparent to whom. Okay, so let's actually do a, so let's actually analyze this example. So I'm assuming that everybody is familiar with this visual. So it's basically trying to fit a line. This is a corresponding equation. How many people in the audience know what this equation is? Yes?
regression.
Actually, no.
Linear regression.
That's not regression. So the equation at the bottom, not at the top. So it's basically an equation to update the weights for a particular neural net.
Is it a decomposition? Is it that?
Variant of that, not exactly. Okay. So the idea is that when you talk about transparency, we have to define transparent to whom. So just the visual itself. So if you know about line fitting, about regression, you would know what that is. So a lot of people would say in the healthcare domain, they would know that. Although they may not necessarily know that this equation corresponds to this particular visual. And then the last one also, that basically until and unless you have that background knowledge, things do not make sense. Okay. So another property is what is known as simultaneity. So which is the property that simultaneously understanding the whole model. So let's take decision trees. I'm assuming that everybody is familiar with decision trees. Anybody who's not? Okay, excellent. Okay, so in general, it is said that decision trees are very interpretable, very easy to explain because you just look at the tree and you know what's going on. However, now think about a model, decision tree versus decision tree A versus B. So both of these are decision trees, but model A is much more complicated. In most cases, for most people, it will take you some time to understand what is actually going on with respect to the phenomenon that is predicting in this model. And we can have decision trees which are much more complicated. So simultaneity is this property that the whole model should be interpretable at the same time. So because of this, decision tree B is transparent while decision tree A is not. Also, another property is what is known as decomposability, which is that the constituent elements of the model should be decomposable or understandable in themselves. So let's actually take two different models. Both of these are regression models. And so if you look at the constituent elements of these models, so age, gender, race, diabetic, smoker, so on and so forth. Again, the performance here does not matter.
these are readily interpretable. So if you look at these features, this data, you will know what it means. Versus now look at another model. So for example, let's say the variable z over here say corresponds to an indicator variable for the person's a, and alpha corresponds to the age, and so on and so forth. So this may be, so in general we tend to think of regression models, or especially things like linear regression or logistic regression and models which are very interpretable. But if you have highly engineered features that you cannot make sense out of those, then you actually lose this property. And that has another very interesting implication, which is that, so now suppose this is the input to your deep learning model, and this is the input to a regression model. So in general, deep learning models are not interpretable or explainable. So now you have a situation where, at least taken holistically, your deep learning model in some sense is actually more interpretable because the input features which are going into that model make sense, while for regression, the features are highly engineered, they do not make sense. So the dichotomy of very simple models like regression models versus deep learning models, that does not always hold. Another property is that algorithmic transparency. So basically transparency into properties of the algorithm. So for example, does it come with certain performance guarantees or not? In general, again, deep learning models do not exhibit this particular property. And then the last one, this is more like a property which is nice to have and not necessarily required, because a lot of algorithms do not, or systems do not have it, which is that the ability to predict that within your AI system, how different parts of the system interlock with one another. So changes are made on one side, how will that affect the rest? So basically feedback and scrutability with respect to the feedback. Okay. All right. So now we come to, say, one particular type of explainable algorithms, or we can also think of this as a scheme to create explainable models. So this particular model is I would say, one of the top two algorithms which are used to create models which are black box, and now you want to extract explanations from them. So the recipe is actually very simple. So now suppose you want to predict particular outcome. So for simplicity, let's say diabetes versus non-diabetes. And let's think of a very simple data space or feature space, two-dimensional. And this is the boundary between your two classes look like. So as you can see, it's very complicated. Your simple models are not going to work. So suppose you have a deep learning model, and because it's a deep learning model, you cannot explain why it's working. So the way that this set of models called line or locally interpretable model explanations work is that, so you take the instance for which you want to predict. So suppose this is there's an instance right there. And what you do is that you take that instance, slightly perturb that labels, put it back to your original model and see what the outcome is, record that, perturb another one, and do that n number of times. So basically now you have n number of new instances. For those n number of new instances, now you create a local model, which could be, say, a regression model. And then you use the coefficients of the regression as your explanations. So basically that's a recipe for to turn any black box into a white box. So the reason that this will work most of the time or much of the time, but not always, is because in some cases, even say at the very granular level, the boundary between your two classes is not going to be linear. So that's where when the assumption breaks down, so does the explanation also breaks down. So in practice, the kind of explanations that you can get are of this form. Okay, so this is an example from actually the original paper. So it's saying that, so you have a system which can identify objects in the system. So now you query, well, why does it think that there's a dog and a guitar? So now it's identifying that, oh, It's saying that it's a dog because of these features. It's saying that it's a guitar because of these features, so on and so forth. Or it's saying that in the healthcare domain, the model is saying that, well, this person has chronic kidney disease because of these following factors, so positively contributing, negatively contributing, so on and so forth. Okay.
Those factors can reach, I can't read them, for the kidney disease. What are those factors?
Okay, so these are mainly associated with the presence or absence of presence and particular values of different labs and white books, aggregated over the course of time. Okay, so the other model with, and I would say this is the model which is used most frequently these days, based on what are known as Shapley values. This actually has been around since the 1950s in the context of game theory, but I would say in the last 5 years or so, researchers in machine learning have also taken up this idea. So again, the details do not matter. So the way that this model works is that it assumes that, or it models that the outcome or the prediction of a model is like a game in game theory. Is everybody familiar with what game theory is? Okay, people who are not familiar with game theory, please raise your hands. Okay. So so a simplified version to say what game theory is, that it's basically a branch of economics which basically deals with scenarios where if you are in a situation where you have to make a decision and there are different outcomes, what is the best strategy to choose? So if you choose strategy A, then this is the penalty. If you choose strategy B, this is the penalty. And then based on basically these penalties known as payoffs, what is the best course of action? So now mapping this back to machine learning. So what Shapley values do is that, well, they say that, well, suppose just like in game theory, when you're analyzing a scenario, so a scenario like that is a game. So now suppose the outcome of a prediction is also a game. And individual factors are analogous to people. So when I say factors, I actually mean your features or your data. So it models that, well, if only one feature was present, what would be your outcome? If two features were present, again, if you have a number of features, then this would be the unpairwise comparisons 3, and pairwise comparisons for 3, so on and so forth. What's the outcome? And then based on that, it does some differential using the formula in the previous slide, and it determines what the contribution of each factor is. And as you can see, if you have 1,000 features, then the number of comparisons would be extremely large. But luckily, there are actually ways to greatly reduce the number of features. One really neat thing about this particular method is that it comes with theoretical guarantees, while the other method that I described, Lime, it does not come with theoretical guarantees. Alright, so when it comes to deep learning, so in general, deep learning models are not transparent. There are a number of ways around that. So you can use some of the two models that I described to extract explanations that do not always work, and towards the end I will describe why these two models do not always work. And then there's another class of models known as mimic models, which we shall discuss later. So that was transparency. So now we need to move on to domain sense. Basically, the explanation should make sense within the domain. All right, so now let's look at our scenario. So going back to our protagonist, Catherine and her doctor. So they're looking at another problem, which is the problem of predicting ED census, or number of people within that particular hospital system. And what they discovered was that the factors that they are looking at, so they are relevant, but then they are not very actionable. So how do we address that? So one thing to learn is that explanations are role-based. or they should from an engineering perspective. So if you have the same machine learning model, if you're providing, say, explanation to a physician, that is going to be very different as compared to, say, the explanation that you're providing to, say, a person who is responsible for, say, management of beds in a particular ward. Even though the underlying machine learning or AI model would be exactly the same. So that's where the role-based nature of explanations come into play. So another thing to remember is that, which comes often, is that in many contexts, explanations should be actionable. So what do we mean by that? So now suppose you have, say, an AI model which works really well, and it's also explainable. And so now you give that to a physician, and then the top, say, let's say, congestive heart failure. So the top factor for prediction is age. Well, the person is 96 years old. Okay. The second factor is male. And so the physician will say, well, this is not very helpful. This is not very useful. I mean, anybody, you don't even need to be a doctor to say that. Well, the person is 96-year-old male with a particular background that he or she, that in this case, he is at a high risk. So what, in a lot of cases, what the end user, what the physicians or the healthcare personnel are looking for is actionability. Again, actionability is not causality. That's an extremely subtle point. So let's look at, so based on that, we can talk in terms of a taxonomy of factors. So there are certain factors which are immutable, so not changeable. So like person's age, gender, ethnicity. So mutable, but not intervenable. So like person's heart rate, so it changes. Marital status. So if for some reason your model says that, well, the top factor for that person having kidney disease is that person is married, well, you cannot really change that. I mean, you could, but not recommended. That was a joke. Okay, there are others which are intervenable. So something like, say, a signal, something like, say, the top factor, or one of the top factors is a person's temperature. Then maybe you can give that person some medicine and then change that. Because your machine learning model is saying that that person is, say, in the emergency department and this is the top factor. In certain cases, that factor may actually be a proxy for something else. Maybe the person has temperature or high fever. But that's not because of cold or something else. Maybe it's because of some other condition. So maybe that person has something called appendicitis, and that person actually needs an operation, appendectomy, to do that. And then there are others which what are known as post-intervenable, which is basically your model says that person is at high risk because they are lacking, say, flu immunization. Once you give that person immunization, if you put it back to the model, it's still going to predict because it takes some time to actually update the model. So this is the basically the taxonomy, or what your end user is looking at. Okay. Another really interesting, challenging part is building models is that just interpreting the prediction of the model itself. Okay. So now suppose you have a classification model, binary classification, so two classes, again, let's say diabetes, non-diabetes, or risk of readmission high versus low. And you build a classification model. So most people intuitively think that because the output of a lot of these models is in the form of probability, a number 0 to 1. So if it's saying that the person has, say, diabetes or cancer or whatever, it's going to be for any values from 0.5 or greater. In reality, actually, that's not the case. So in reality, how these boundaries are made is as follows. So what your model is going to do is going to output some probability. We actually call that score. So it's a particular score from 0 to 1. And based on that, based on some metrics, say precision or recall or F-score, it is going to optimize for that metric. What is the cutoff value for the score should be so that your performance is maximized. it could be the case that for all the values, say greater than 0.35, that's everybody with high risk of diabetes. So the intuition that most people have, anything greater than 0.5 or greater, that actually does not hold. But even beyond that, so even if you have a gradient, say 0.35 to 1, if you have a score like 0.6 to 1, what does that mean? Does that mean that that person is at medium risk? Does that mean that that person is at high risk? So from the domain side, we have to impose an interpretation that this constitutes medium risk, this constitutes high risk, so on and so forth. Okay, so another point which I have alluded to earlier, and I'll emphasize this again because one cannot emphasize this enough, is that when we talk about actionability, actionability is actually not causality. Also, for certain explainable models, we may actually not get actionable predictions. And even when there is actionability, there may be some temporality associated with it. So if your factors, if your model is saying that, well, that person is high risk because of immunization, then, well, you just give a person a shot and you're done. Versus, say, your model say that person has a high BMI, body mass index, could be because they have an unhealthy lifestyle and you need to fix that. Well, you cannot fix that right away. It may take months of intervention to do that. So there's the temporal aspect of that one needs to account. Okay, so which brings us to another interesting class of models known as GAMs. So anyone who is familiar with GAMs already? Okay. So these are what so GAMs are generalized additive models. The idea behind these, so these have been around at least since I would say late 70s, early 80s. Idea is very elegant and simple. So you have some outcome variable and some features or data, so n number of features. Okay, so the way that you model or build a model is basically with respect to your outcome. If you change, say, your first feature, how does the outcome look like? Second feature, third feature, and number of features. And then you do an aggregate model, and that's basically a model. So it turns out that and because you can visualize that these are interpretable. The downside is that there are certain types of complex phenomena which they cannot model because they make certain assumptions about the model. Okay, so it turns out that you can actually create better models based on GAMs. So these are known as GA2Ms or generalized additive models with interactions. So the idea, we just saw this idea a few slides previously, so which is basically that, well, instead of modeling just one particular feature with respect to the outcome, what if we model all pairwise features? And again, there are ways to reduce the space and speed calculations. And of course, you can also consider 3, 4, so on and so forth, but it just becomes very difficult from a computational perspective. It turns out that these models, GA2Ms, not only are they very interpretable, they also have really good performance. So again, without even going beyond interactions between two variables with respect to the outcome. Okay. So this is an example of what the outcome looks like, or what the output from these models look like. Okay. So let's look at this example. So x-axis is the age of the person. Y-axis is the pneumonia risk score. So what this model is basically saying is that up until the age of approximately 50, the person's risk score is somewhat stable, then it starts increasing, then there's a jump around 70, another jump around, say, 85, and then there's a decline around 100. Okay. So if you show this to a clinician, just by looking at the visual, they'll be able to make sense of it, and they'll see, okay, and they'll agree with the outcome. And then you can do this for any n number of variables. So let's actually do an exercise. So here, So the function seems to be monotonically increasing and then it declines. So just by looking at this slide, can anybody guess why are we seeing a decline over here?
That's people are dying at this stage, so there are a few number of patients.
That's exactly the reason. So basically, if you look at the data here, it's not that the risk decreases, it's because we have access to fewer people in that side of the data set. So basically, if a physician is looking at this and they know a few things about statistics, they will also be able to capture this. Again, very easy to explain. So even if there's an epiphenomenon like this, you can catch this just by the visual. So like all the math that we just saw, you don't really need to know that. Again, relatively easy to implement and understand.
What do you mean by the second sentence?
Okay, so second, it refers to this particular pairwise comparison. So if you have 1,000 variables, then you may have to do n combinations of or pairwise combinations of 1,000 variables. That's a very large search space. So there are ways, some theoretical results which show that you can reduce that pairwise comparison.
If the system is really, so we have similar things in physics. If the system is really strong interacting, then not only the pairwise interactions will be important, but also even like 3 feature interactions, 4 feature interactions.
Yes, correct. You're correct. So the people who came up with this, so they also mentioned this, the idea of like 3-pair interactions of 4, so on and so forth. But then this computationally like not tractable. So and even the pairwise version gives pretty good results. So why not? Okay, so which brings us to the next pillar, which is consistency. So consistency is basically the idea that explanations should be consistent across different models and across different runs of the model. So for the sake of time, I will really focus on the domain part. Okay. So let's look at an example of consistency. So now suppose we have a machine learning model. So the model predicts, say, length of stay in a hospital. So how long the patient is going to stay. And so our hypothetical patient, Harrison Wells, age is 72. He has COPD and chronic liver disease. And again, the prediction itself is less important. So now we use a there are 3 different machine learning models to extract explanations. So the first one is that we look at the explanations at the level of the whole phenomenon. Okay, so what do we mean by that? So for the machine learning model as a whole, what are the top factors for predicting, for the prediction? So an example of that would be that, so if you have a regression model, then the ranked list of regression models, that's basically your top factors. Okay. So now suppose these are the factors that you get, and then there are other models. There are other ways to compute this. Things like information gain, for example. Okay. So now this is your ranked order list at the level of the phenomenon for your whole data set. And now these 2 ranked lists, so these are for this particular patient, Harrison Wells. So if you use Lime, Lime is saying that this is the rank list, and Shapely values, that's the other model that we talked about, this is the rank list. So now a couple of things to notice. So one is that for the individual, the rank list is different from the population level. Again, that is to be expected because not everybody is going to be the same. Also, another thing to note is that even if you don't know the meanings of many of these things, like say chronic condition anemia, so the color corresponds to the same feature across 3 different lists. That's the main thing to focus on. Okay. the rank list across individuals is different from the global population, but also look at the other thing, other phenomenon, which is that for the same exact prediction, these explanation models are giving a somewhat different rank list. So the question or the research question that is posed is that there should be consistency across models. So the explanations say that you get from Lime versus Shapley values, at least to some extent, they should be consistent with respect to one another, what the explanation of the phenomenon is. Okay, so it turns out that when it comes to consistency, or trying to find consistency, or trying to determine what a better explanation is, there is actually no agreement in the literature or in the field. So this is actually an active area of research. Okay. So another thing one thing that researchers have noticed is that, especially for methods which give out a rank list, so we talked about Lime, we talked about Shapley values, there is already a whole body of literature around how to compare rank lists. So we don't have to do anything new, we just take that and then just compare those as just another way of comparing rank lists. And the reason is that A, it's well known, and B, so even if there is wide disagreement, then we can actually quantify that wide disagreement.
I didn't get what those numbers were on the table. So we have different models.
Okay, I should have mentioned. Okay, so we have different models. The values of corresponding to these variables, that's irrelevant, so that's why we have not given those. So we have model A, B, and C. And so model A is saying that age is the most important one, gender is the second most important one, diabetes, so on and so forth. Model B is saying is that age is most important, and person being a smoker, test is the second most important feature. While model C is saying that being diabetic is more important than being alcoholic. So all of these models, these explanation models, they correspond to the same prediction, or same prediction.
Same prediction about with the same performance, or
same? Okay, so same prediction for the same instance.
Okay.
So is there a marker? Okay. Okay.
Okay, so they made the same prediction, but they have different explanations. Now.
Okay, no, okay. Let me actually correct the question slightly. I think I know where the confusion is coming from. So the explanation models that I just talked about, so especially Lime and Shapley values, so these models do not make predictions themselves. So the way that they work is that you have a model which makes predictions, and you take the prediction of the model and then combine them with the explainer model, say Lime or Shapley values, and that explainer model comes up with an explanation.
I think you are expanding the explanation in terms of, let's say, Shapley model in terms of those shapes. So basically, it's a projection on that.
That's one way to think about it.
On those shapes, or in something like Fourier transformation.
That's a rough analogy, but we are doing something similar. Not exactly, but that's a rough analogy. So basically, to summarize, the prediction model and the explanation model may be different. In this case, we are only focusing on the cases where the prediction model and the explanation models are actually different. So this will not apply to something like a decision tree or a regression model, because the prediction and the explanation are exactly the same.
I have one more question. So I think this is important for the doctors, right? They want to know why actually this prediction is being made by the model.
Correct.
So, and then they're going to look at different models, and they're going to say, okay, this model, the first one says the age is the model that says age is the most important thing in this prediction, but model C says age is actually one of the least important factors in this prediction. So who's telling the truth?
Yes, and that's it.
And is there a way to find out?
And that is exactly the next slide.
Okay.
So, good thinking. All right, so there are two main ways to evaluate explanations. So one is wild humans, the other one is you figure out some way to automate that. So now let's focus on how can we use humans? Okay, so basically, so let's take the three models, give that to domain experts, physicians, and then ask them which explanation is the best. The main issue is that that technique does not scale well because again, physicians are very busy people. They don't have enough time to go over thousands of use cases. There are ways around this. So again, as I said, this is an active area of research. So I'm actually working on a paper just on how to evaluate explanations. And that does involve also involves, I should say, manual evaluation by physicians. So take the same prediction and then give that to different physicians and then ask them. And then you can to make things interesting because of things like automation bias. So for clarity, I just described what automation bias again is that over the course of time, people can get habituated when using computational systems, not just AI or machine learning, start treating that as truth. So one version of running these experiments is that you actually give, when you're trying to compare these models, you also give random rank lists to the physicians just to see if they're able to catch that or not. Or if you want to be really sneaky, you can actually reverse the order of the rank list and then show them the worst and then ask them. Again, so that you don't run into that, the problem with respect to the automation bias itself. And then also you get these evaluated by not just one physician, but by multiple physicians. The other way to do that is that, again, as I mentioned, these are rank lists, and there's a large body of literature on comparing rank lists. So if you go to, say, a domain like creating recommendation systems, there are literally dozens and dozens of papers. So you just take that literature and compute some course between orderings of the data. So concordant pairs are basically pairs of instances which are basically same relative rank. And then you compute that, and then you basically put them in this formula, and you get some number. And then there are different variants with respect to that. Again, the individual constituent elements of the model, I would say, are secondary. Okay, so now we have talked about some aspects of, or some properties of explainability, and then using that to create responsible systems. So now actually talk about counterexamples. Okay. So now let's suppose we have a use case where, say, let's think about, okay, so this use case is emergency department arrivals. So which is that number of people who are coming in the emergency department. So in our case, our main protagonist, so she has a model, a black box model which can predict that. And then she goes to the planner of the ward and she says that, well, I have a black box model. And I have this other model which is more interpretable, but its performance is low. And the end user will say that all that I care about is an accurate model which can tell me what is the number of people expected. The risk of getting this prediction wrong is actually not very high. So if that's the case, then you actually don't need explanations. So you can just skip that. The other one is that if you have models which have near perfect performance, so an example would be Google's famous model which can predict diabetic retinopathy. This also comes with certain caveats that even with the examples we saw that it's still possible to fool the model. But in general, the rule of thumb is that if you have a near perfect model, then you can live with it. And that has actually been the first model which has been approved by the FDA to be put into production. Okay, so the third use case is that you have a model which comes with theoretical guarantees. That theoretical guarantee is basically that given the following distribution of data, your performance will always be greater than X, whatever that X is. It turns out that for most real world problems, this never happens. And when I say most, I actually mean almost all. real world problems, if not all. So this is, at least for now, this is more like a theoretical dream. So maybe one day, maybe tomorrow or 10 years from now, there will be a theoretical breakthrough, but until now, this is more like a hope. Okay, so then the counterpoint to that is that, well, when we talk about explanations, in the real world, with respect to humans, most people cannot explain why they do certain things. If you ask them, they'll just make something on the spot, which may or may not correspond to how they're thinking. A lot of human reasoning is unconscious. So then why are we expecting these models that we're building who may just be too complex to begin with? And then the last argument is more of, you can also think of it as an argument about the future. So this argument is that, well, why are we using computers to begin with? In healthcare or in general? Well, it's because there's too much data and the computations which are required, it's not possible for people or even groups of people to do that, at least in a timely manner, without errors. So if that's the case for computing in general, then why are we using machine learning or AI? Well, again, same thing, lots of data, humans cannot process it. So maybe that also implies that is that there are models, if not already, maybe in the future, which are just too complex for humans to comprehend, ever, or even groups of people to comprehend. If that's the case, then as asking for explanations is actually trying to simplify the phenomenon. Maybe we can never get explanations out of those because humans are just not equipped to understand the complexity of those models. So that's another argument that certain people think. In fact, there's actually a book that came out which argues exactly that. So, okay, so here, so in that particular argument, the particular argument is extended that, so think about, so the way to think about creating responsible systems is not necessarily by explanations, but by converting that into a practical engineering problem. Okay, so think about the following. So the vast majorities of mechanics in the world, because vast majority of mechanics actually live in developing countries. So think about, say, sub-Saharan Africa or a place, say India or Bangladesh. If you go to a mechanic, most mechanics do not have an engineering degree or even have gone to high school. Many of them may not even know how to read and write. So when you go to a mechanic, you do not ask your mechanic, so do you know the second law of thermodynamics? And although it may be the case that, it's actually the case that, well, the second law of thermodynamics can help you understand how the internal combustion engine works, which drives parts. But you do not ask that question to your mechanic. You just expect them to debug whatever the problem is and fix it. So maybe that's the approach that we should adopt with respect to AI systems in general. Our ability to debug these systems and fix them. So that's another, I would say, somewhat growing camp in this discussion around responsibility and explanations. So without making any comment regarding which camp is right or wrong, but again, food for thought, something to think about. Okay, so let's do another quiz. So what is the scenario when you may not want explanations? So theoretical guarantees, better than human performance prediction, whenever I want. 0.7 area under the curve. There's a story behind this, which I'll discuss later. E or F. So A?
It's E.
Anyone agrees with that? Yes, that is the correct answer. All right, so that would be a natural way to basically, okay, so take a break. So just to summarize. So we have talked about explainability, transparency, and then different aspects of explainability, transparency, domain sense, consistency, and counterexamples. And in the second half, we will talk about parsimony, generalizability, trust, and fidelity.
Okay, so let's give it a break for 15 minutes and come back at 5:35.
All right, folks. So welcome back to the second half of the tutorial. So in the first half, we talked about three main aspects of what constitutes explainable AI in healthcare, as well as counterexamples where the argument is that you actually do not require explainability. And in the second half, so we will focus on 4 different aspects of explainability. So let's start with the first one. Parsimony. So the idea behind parsimony is that explanations should be as simple as possible. So that applies to the phenomenon itself and the model as well. Okay, so how many in the audience are familiar with the Occam's razor? Or heard about the Occam's razor? So in science in general, so we are talking about outside the scope of machine learning, AI, but science in general. So one of the foundational principles of science is Occam's razor, where the idea is that if you have multiple explanations for the same phenomenon, and again, it doesn't matter which phenomenon it is, say planets orbiting around the sun, gravity, forces, so on and so forth. If there are multiple explanations, then the explanation which is the simplest, can be defined in terms of one that involves the presence of the fewest number of things. That explanation is the best. So that's how science works. If you were asked to summarize the foundational principle of science, that's what Occam's razor is, named after a monk from the 13th century. So in general, that's true in biology, physics, chemistry, so on and so forth. So in healthcare, there's a semi-humorous rebuttal to that, which is that known as the Hickham's dictum, which says that a man can have as many diseases as he damn well pleases. So what do we mean by that? So the Occam's razor basically says that given a particular data, say related to a person's condition, person's health, you can form multiple hypotheses, and the hypothesis which is likely to be correct is the one which is the simplest. So what Hickham's dictum alludes to is, in reality, in healthcare, what happens is that given the data, there are actually multiple things which are possible, and based on that, you simultaneously form multiple hypotheses. Based on that, you gather new data and again refine multiple hypotheses up until you reduce your space of things which may be possible. So an analogy which is used in healthcare by physicians is that, so suppose you are, say, standing somewhere and you cannot see the animal, but say you hear the neigh sound, which in English is for a horse. So the first thing that comes to your mind is, well, it's a horse. But it's also equally plausible that instead of a horse, it's actually a zebra. But because we are familiar we associate that sound with the horse, that's the first one that you think. So basically, this is an example of hearing that sound and then having multiple hypotheses. It could be a horse, it could be a zebra. So that's true. So now if we use this analogy and move to the healthcare, that's how most healthcare, how most medicine is done in practice. So basically, our general framework of how science is done that applies but not exactly. So in the machine learning domain, or in computer science in general, so people also talk about the Occam's razor. So there's even a principle known as the MDL, or minimum description level. So we don't need to go into detail regarding that, but there is also an analog of that in machine learning, which came out in actually 20 years ago, which is the idea that Occam's razor in machine learning, that if you have multiple machine learning models with almost equal predictive power, then choose the one which is most explainable. So that's what is known as the Occam's second razor. That said, another thing you have to notice is that, so your machine learning model are going to be based on data which is available. So there's parts of the world about which you're not collecting any data, oh, your model cannot do anything about it because it's not visible to it. In practical terms, what that would mean is that, and of course, when you build predictive model, get explanations, then the simplest explanation may not be the best because that's not part of the data. This is actually a real world example that we have actually encountered, which is that so you build a model, you get a prediction and show that to a physician or say even a nurse, and then they ask the question, yeah, your prediction, and the comment, your prediction makes sense, overall performance is good, but why is that particular factor not in your prediction? And I know from experience that that's extremely important for this particular phenomenon. But the reason for that is that it is because that particular aspect of the data is not being captured, or is actually not in the data per se. So this is where things get really interesting in practice. Because if that factor, which say that physician is always used to thinking, if your machine learning model is not saying that that is an important factor, they may actually distrust your model. They'll say that, well, this particular factor, I'll just make up something, let's say, this particular vital or this particular lab is not an explanation. And you'll say, well, that's because we don't have data. Regardless of how good your model is, and I've seen this in practice, I've had conversations regarding this. The physician will say, I don't trust your model. You should go back and incorporate that. And it may be the case that, and there are real world examples, even that you incorporate that, so you spend, say, 3 weeks doing additional data engineering, incorporating that factor, and you realize that the performance either does not change or changes in a very negligible manner. And then after that, so the physicians say, okay, now I trust your model. Although the performance is still exactly the same. If that was just a problem, then that would be fine. But practically what happens is that, so now you talk to another physician in the same hospital system, and then she says, oh, this is very interesting, but there's another factor that I'm always used to seeing that is not in your model. So what's the practical implication? So now you again have to go back to your sources, do some data engineering, spend 3 to 4 weeks, and again you see that you are not getting the performance boost. Again, that's in terms of, again, implementing these models and getting people to use them, that's a real world issue that we see. So again, this is not just a theoretical exercise. Another thing to note is that machine learning models, at the end of the day, they're based on the data. The focus is on performance. And one of the examples that I gave in one of the previous lectures was that you can actually use data which you may think is nonsense, but it may be processed for something else. So a really good analogy is that, so especially if you think about how history of science is taught, so I'm familiar with at least the US in high schools, is that, so how traditionally people had this geocentric model of the universe, that the Earth is at the center of the universe and all the planets in the sun revolve around it. And then Copernicus came up with this new model. In practical, and it was adopted because, well, it had better predictive model and it was a superior model. That's actually a false narrative. If you look at the predictive power of the models, at least up until Kepler, which is almost a century after Copernicus, the older model that the Earth is at the center of the universe actually had greater predictive power as compared to the simpler model that planets revolve around the sun. So again, the idea being that the simpler model is not always the best. I mean, you can even have the model that the Earth is flat, and that's a simpler model, but again, that's not necessarily the correct model.
That's what we use in maths.
Yes.
2-dimensional.
And it's useful for maths, for navigation. Okay. So another related concept is.
Can I ask you a question?
Yes.
So you said something like maybe someone may say, okay, I don't care about explanation, what I care is the prediction. if I predict the disease, length of stay, or end of life, then I'm golden. I don't really care about the explanation. Someone may say that. Okay. So, but without the explanations, can we be sure that the prediction is actually not accidental, but real good prediction?
Okay, so there.
So
Yes,
the
yes.
prediction, so the prediction that the model does, it may be just accidental, right?
Yes, and the great thinking was that is exactly this slide.
Okay.
All right, so basically what you're saying can be summarized as being right for the right reasons. Okay, so this particular example it's not from healthcare, but it's a very good illustrative example. So so the problem that we are dealing with, machine learning problem, is so in the domain of text classification, which is basically the domain that if you have a large amount of text, you want to categorize individual text where, and text could be, say, a newspaper article or say an email in different categories. Okay, this is from a famous data set. It has like literally thousands of emails, and now you want to classify these into different categories. So in this case, they created a machine learning model, and that model is not supposed to classify these emails into different categories, and this falls under the category of religion. And in general, so the prediction works, and of course it makes sense. I mean, people are talking about Christianity and also about atheism. Okay, all right. So now, but if you look at the factors for prediction, so one of the top factors for prediction is this, .edu. So basically, if the email is originating from .edu, then the model is saying that the email is about religion. So basically, if you're sending the data, if say a new data set came from this university and it was Istinye.edu, then regardless of whatever you're discussing, the model will say that, well, you're talking about religion. So the model is right, but it's not right for the same reasons. Why is it making this mistake? Is because for this particular data set, overwhelming majority of the articles that came or that were used and discussed religion originated from a .edu address. So you can actually use this to debug your code and fix that problem. So that's one. The second part is that, so this discussion that I only care about the performance, I'm not really concerned about explanations. So that works in scenarios where the penalty associated with being wrong is not heavy. So going back to the example that I gave earlier, so if you're a discharge planner for, say, a general ward, and you want to know how many staff members do I need. So even if you're off by 2 or 3, and you're wrong, that's fine. You're off by 2 or 3. Versus if you want to predict, if your prediction model is somebody has, say, a particular humor or not, then when you're off, then the penalty is really high. So in those cases, there's actually an article that came out in Nature a few months ago where the author argued that for high-stake predictions, regardless of the accuracy of your model, regardless of their performance, you should not use a black box model. And that's also the view that I also hold, because again, the penalty can be really high. And there, of course, there are a host of use cases between these two extremes, and you address them on a case-by-case basis.
And also the other thing, I think you can fit any you can even fit a wrong model to the data by adjusting, tuning the parameters, I guess, always.
Yes, of course.
With the AI in general, I mean, are we looking for the known things, for the described things, and using the AI just because to speed up and have accurate data result? If I'm looking for unknown and something else, I mean, if I'm, for example, in the healthcare, okay, we have spoken about the we will have a solution that we use the radiology images, and there is also reports regarding these images. And the reports will reflect always what the doctors, the practitioners learned at, on their education and what they have practiced at actually. But the image could tell us something else. I mean, what is the right model then? For what purpose we will have the AI solution?
Correct.
So I think the model depends also what we want to address. What is the goal at the end of the day? What we want to reach? To give to the practitioners an easy way to analyze the images, or to find out actually what they didn't learn during the life.
Correct. And also in that case, so if you already know something, then a supervised learning approach, so the cases that we're talking about, that's more appropriate, versus if your analysis is exploratory in nature, then an unsupervised approaches would be much more appropriate.
So we can compare this.
Correct. Okay, so that brings us to the next pillar, which is generalizability. Okay, so now going back to the use case that we are talking about. So the physician, so he looks at some instances and he realizes that the instances do not generalize. And so within generalizability, so we can talk about generalizability at the level of individuals, at the level of cohorts, at the level of populations. Now let's start with models. Okay, so explainability, so we can talk about models that are generalizable locally. Or applicable only at the local level, so which is at the instance level. So we are generating explanations for each instance. So I will take the analogy to healthcare. So the explanation for the predictions that these models come up with, they would be explanations for individual patients. They would not be applicable to others. So the Lime and Shipley models that I talked about earlier, that would be examples of that. Then there are cohort and global level models. So one explanation for the whole phenomenon, and if you want to get explanations for individual instances, you can use the same model to do that. So decision trees or GAMs, so that's examples of those models. So now there's also generalizability at the level of algorithms. So we talk about model agnostic versus model specific versus class specific models. So model agnostic explanations are that models that you basically apply them to practically any machine learning algorithm, any machine learning predictive algorithm, I should say. So again, going back to the two examples that we have been talking about, Lime or Shapley values. So if you have a decision tree, if you have an SVM, if you have a gradient boosting model, or even a deep learning model, you can combine those with a prediction you can take the prediction from those, feed it to any of these two models, and you will get an explanation. And then there are certain models which only work with a particular class of models, so only like tree-based models, for example. And then there are others which are very specific. And when we say very specific, these are basically models where the predictive model and the explanation model is exactly the same. Okay, so there's also generalizability at the level of the data. So you can say that in general in your data set, what are the variables or features which are more relevant to the predictions? In this case, let's say length of stay. You can also talk about prediction at the level of prediction. So why are certain patients being predicted to have certain types of behaviors, and why do certain patterns belong to a particular model? So the other general thing that we can talk about is We can classify or talk about generalizability in terms of the model output. So the vast majority of the models that we have talked about up until this point have form like this. So you have a prediction and then the relative variable importance. So the most important is age, gender, then diabetes, so on and so forth. But then there are also models known as rule-based models, where your explanation will look something like a set of rules. So let's say age is greater than 55 and it's a male and it has COPD, which is a lung-related condition, and there's complication, then that person has a longer length of stay. And decision trees of this form, they're also rule-based models, so it's possible to convert any decision tree into a set of rules. And then lastly, case-based models, they're not used as often, but for certain types of end users, these are most relevant or most useful, especially if the explanations are very complicated. Which is that, so if you predict that, say, somebody has a particular disease or a condition, the model will not tell you, well, it's because of factors A, B, and C. It will just say, oh, I think that that person is going to have this disease because this patient is like these other 3 patients who have had this disease. So these are what are known as case-based models. Okay, so let's do a quiz just to ensure that everybody's awake. So why would one not use the simplest model? It may not generalize. It's because you like complicated models. The model is right for the wrong reasons. A, B, B, and C.
Definitely not B.
B, yes.
Not B.
Yes, so it's actually C. Okay, so which brings us to the third part, which is trust, or rather fostering trust and performance. So the idea is that even before you can talk about explanations, you should first focus on trusting the prediction itself. So what use is an explanation if you actually do not have a model which is sufficient amount of performance? So it's basically the expectation that the predictive system has sufficiently high performance. And that can be described in different ways. So say precision, recall, area under the curve, so on, whatever your favorite metric is. Because the reason is that if you have explanations but a subpar predictions, then of course that's not going to foster trust. And then especially if you have a model which may lead to wrong types of actions, then your end user is not going to use it. So one really interesting use case where things get complicated is that where you actually do want to first address this is that you do want parity with respect to human performance. So basically, if you have at the very minimum, you want to have a model which can do as good as humans, because then otherwise, why use AI or machine learning to begin with? Now the complicated part is, so now suppose you have a model which in general does not do well as compared to humans, but there are certain parts of the data on which it does better than humans. Then in those cases, that's a reason to actually use hybrid systems, where you basically use one machine learning model to identify the parts of the data in which your model is going to do better than humans. And then on those parts, you use predictions from that model and not the output from humans. Okay, so that leaves us to this trade-off, as we have talked about that in the past. Letter completeness, I'll define this again. This observation that in general, there is a trade-off between interpretability or explainability and the performance accuracy. X-axis could be any performance metric. So basically, linear regression in general, these are highly accurate. You can just look at the linear coefficients and coefficients associated with the equation and understand what's going on. But they are, in general, they're not very accurate. On the other extreme, they are neural networks, deep learning models. They're not very interpretable. And I should mention that this visualization is based on somewhat like consensus in the field. It's not based on people running hundreds and thousands of experiments and summarizing the results, but it's a good representation. And then same visualization we can talk about in terms of the complexity of the model. That the really complex models, if you look at the number of parameters that they have. So the x-axis is actually a log scale. This is one. This is let's see, 10,000, 100,000, so on and so forth. So again, deep learning models are extremely complex, and the y-axis is accuracy. Okay, so now coming back to the question that Shannon asked previously. So this is a visual representation of how we choose. So there are two dimensions. So there's the accuracy of the model, there's explainability, and when you want to choose a model, the third dimension that we consider is the risk associated with the decision. So if the risk is high, then we forego explainability and then just focus on interpretability and vice versa. Okay, so another thing to remember to remind ourselves is that explanations are not associations. That said, there are certain models, especially used within the domain of deep learning, which do exploit this fact. Okay, so the main idea behind these models is that so think about a system which describes an image. Say an image of this classroom, and now you want to come up with an explanation. So what these models, and there's some accompanying text. What these models will do is that they will look at correlations between objects which are detected in the model and words that occur frequently. So the assumption is that there's some correlation, so when they give out these explanations, they will exploit these associations and give those as explanations. Again, that's a proxy for, basically you can think of that as a poor man's versions of explanations. Things, again, not perfect, but it's better than not having an explanation at all. Okay. So the other thing is that, so another thing that we talked about in the previous lecture, is that you can still have really accurate models, but at the end of the day, machine learning models exploit correlations and correlations with respect to a particular data set. So the manner in which a human is recognizing images or objects or phenomena in general is almost certainly not the way that these AI machine learning models are working. So here are some examples of basically, each pair example corresponds to the same thing. So a machine learning model thinks that this is a school bus and this is also a school bus. This is a peacock and this is also a peacock. Again, not very difficult to fool the machine learning system. And again, this is one of our favorite examples from yesterday. That a machine, it's again possible to fool a machine learning system to think that this muffin is actually not a muffin, it's actually a kind of a dog.
Is it possible to teach that this is not a dog?
Yes, so for that you have to add that in your training set. If you just add these so if you label these as dogs and put them back in your training set, then sure. But then the counterpoint to that would be that somebody else would come up with, may presumably come with counterexamples to other things and then put them in your data set. But yes, it is. So the idea is that these are black box models, and even if you have models which are extremely accurate, have superhuman performance, because we don't know what they're learning something, that's for sure. And what they're learning is different from how humans learn. We can still we can figure out ways to fool them, and especially if it's a malicious actor who wants to say actively harm people, then yes, it is possible for them to do so, using the right approach, of course. Okay, so which brings us to the next pillar, which is fidelity. So fidelity is the idea or the expectation that the explanation and the predictive model will align with one another.
It basically means no accidental models, right? So
That's
the
one way.
So the
Yes, that's
predictions
one
are
way to think about
not happening, or yeah, good predictions happening with
it. Good.
educated, good guesses.
That's one way to think about it, yes. Okay, so coming back to our example, so basically our physician, so he's examining the explanations for, in our case, risk of readmission, and realizes that the explanations are not correct. And so the machine learning experts, they rule out non-determinism from their algorithms. They realize that there's some problem with the data pipeline, so that's why we are seeing this. So what does that? Okay, so that's a practical example. And so there are a number of reasons why we can lose fidelity. So let's start with the first one. So data provenance, which is basically where's the data coming from. So maybe there are some issues with respect to, say, instrumentation or how the data is being captured. There's censoring of the data. So say before a particular point in time, the data is just not being collected. And again, at the end of the day, your machine learning models are only going to capture what is in the data. So there are certain aspects of the real world which are not captured, and well, those are not going to show up as explanations. And also there may be shifts in your data distributions over time, and because there are shifts in your distributions, then the phenomenon may change, and because of that, your explanations may actually be incorrect. So another example that we talked about yesterday, so which was that you can actually build machine learning models which predict risk of readmission using these phases of the moon as a feature, as one of the data points. And the reason that works is not because astrology is correct or the moon is influencing the behavior of people. We can believe that, but at least that's not the case, as far as we know. But it's because the phases of the moon are proxy for another phenomenon, which is the amount of light at nighttime, and especially in parts of the city which are not well lit. When people get drunk, the likelihood of accidents is greater, which results in more people being part, or more people ending up in emergency departments. So that's why this works as a feature. So there are two related concepts that we can also talk about when it comes to explanations. So there are the soundness and completeness. So they come from logic. So an explanation is sound if it adheres to how the model actually works. Completeness is if it encompasses the complete extent of the model. So it is actually possible to have one without the other. And models can their soundness and completeness can actually vary. So let's actually see where that can happen. Okay. So the other distinction that we can make with respect to fidelity is with respect to what are known as anti-hoc models and post-hoc models. So anti-hoc models are basically models where the predictive model and the explanation model is the same. So ante meaning before and post meaning after. So post-hoc models is models where the predictive model and the explanation models are different. So after the fact. And because they are after the fact, the explanation may or may not correspond to the phenomenon in question, or the degree that by which they correspond to one another will vary. So one practical implication is that model agnostic methods like, say, line or shapely values, so you can use them with pretty much any predictive algorithm, they will work. They're very generalizable. From an implementation perspective, if you are thinking in terms of having a machine learning pipeline, they are extremely useful. But because they won't always have fidelity, so there's a possibility that you may get slightly incorrect explanations. The positive side is that you can use those with complex machine learning models and they will work. The downside is that they will mostly work. Mostly does not mean always. So then you can flip the things around and you can say, well, let's actually use models where the first type of models, which are anti-hoc models, where the models and explanations are the same, and that's the ideal world. But it turns out that that doesn't work because of the same reason that these usually correspond to models which are not very complicated, and because of that, you don't, in most cases, in most real world cases, you do not get a high enough predictive performance. So there's that trade-off again. There's a third class of models known as mimic models, which are very interesting. So in the literature, people call them student models, shadow models, surrogate models. It's referring to the same exact thing. Idea is very simple and elegant, and it's surprising that people did not think about this 30 years ago. So the idea is as follows. So you have some training data, and you have a complex model. So let's say it's a deep learning model. The details do not matter. So you take your training data, you have some outcome. Let's say the output is diabetes, not diabetes. Okay. So build a complex model, and well, it's a black box model, so you have no explanation. What can you do? So you can build mimic models, and the way that mimic models work is that, so in your original model, you had some data and your outcome, which was diabetes, not diabetes, your ground truth or the reality of the condition. So now you build a new model, let's say a decision tree, or even say a regression model to simplify discussion. You take all of your training data, but instead of taking the ground truth, so let's actually use the next visual. So this is your data, X, Y, it's your ground truth. You get the output. So the way that you build your mimic model is that you take your original data set, which in this case is X, and you take the output from your complex model in this case. So this is basically prediction, diabetes, not diabetes. This is the reality. And you take the prediction from your complex model and use this as your new target, as you inputted this new model, and you get new predictions. And this is a more complex version of that. We can ignore this for now. Okay. So in reality, so here's the thing. So in reality, if instead of a deep learning model, so let's say this is a decision tree. If you just had a decision tree here, you would have really bad performance. But if you build a decision tree here, then your performance will not be as great as a deep learning model, but it would still be better than if you just had a decision tree on the original data set. The other thing is that there are no theoretical guarantees that this will always work. So it's an empirical question. Certain use cases, you just try this and see. Sometimes it works, sometimes it doesn't work. So that's one. There is one theoretical argument why this works, which is that, so the reason that, say, a decision tree is not able to model this phenomenon is because the phenomenon is very complex. So for any machine learning model, there's some error associated with it. But a deep learning model can model this complex phenomenon. So the output of the deep learning model is not going to be exactly the same. It won't have like perfect performance. Any machine learning model, including a deep learning model, simplifies the phenomenon when it models it. Because it simplifies the phenomenon, now the decision tree can model it. So that's the theoretical argument why these mimic models sometimes work. And when it will work and when it will not work, that's a theoretical question. There's some research going on around that. And to the best of my knowledge, there's no definitive answer. So this is basically one of the things to try. Okay. So the other thing regarding explanations is that, also alluded to previously, was that if you have an explanation, if you have a data set with a large number of missing values, and if you do imputation, which is basically infer missing values using, say, interpolation or using the average in the population, average for the cohort or loss value seen for that person. Then you can still get an explanation, but now suppose the explanation actually corresponds to these imputed values. Then that would actually mean that if you show this to a physician and one of the values is actually an imputed value, then that physician may actually not trust your models because they may say that you are saying that the prediction is because of a factor, because of a reading or a lab which was actually not taken. So I actually argue in one of my papers that you should actually not use, if you want to use explanations, then you should actually not do imputation at all. Okay. So how many people in the audience are familiar with random forests? Decision trees? Okay. So random forests, you can think of these models as being made up of literally hundreds and even thousands of decision trees. And they combine basically the output of all these decision trees in a single model. So there are also some newer models which can actually be used to interpret random forests. And the way that they work is that they look at the contribution of each branch of a decision tree in these hundreds of models and aggregate them. So for sake of brevity, I will skip that. Okay. So there's this scheme. It's slightly outdated, I would say, because there's new work has come out and new algorithms. So this summarizes that different for basically a number of machine learning algorithms. What are the various properties that they have in general with respect to fidelity, model specificity, and scalability of the model? And then you can map this to basically in what kind of use cases, what kind of models you should use. So I'll actually share this with the group. But again, this being the idea is that given certain use cases, it is possible to map the kind of techniques, to the kind of problems, and what types of explainability should be used. Okay, so as always, I'll end up with the same note regarding not just artificial intelligence, but this time also explainability. So again, if you looked at explainability, it is not purely a problem which is just related to artificial intelligence. It is not just a technical problem. And the reason for that is that when we talk about explainability, there's an element of subjectivity. So what is explainable to a person would be different to what is explainable to another person. As you mentioned in the first half, the role of the person is very important. So for the same predictive model, if you're showing this to a physician, your explanation model should be different versus if you're showing the same model to, say, a nurse practitioner or a person who's responsible for staffing in a ward. And the reason for that is that their focus is on something different, so why show them something relevant? And so why do we need explainability to begin with? It's A, to foster trust in our AI models, and B, to ensure that the prediction is actually being made for the right reasons. It's not because of some artifact in the data that is being done. So again, at the end of the day, why are we involving AI or machine learning? It's towards an end, not an end in itself. So that's why it's better to think about assistive intelligence and not artificial intelligence. And so here I will end the tutorial for today. And so there are actually a large number of, I've created a large number of references related literature. So basically around 200 papers related to just explainability in general. And you can also share that with a larger group if people are interested. If there are questions, I will be happy to address them.
Could you please share your presentation with us?
Sure.
Okay?
Yes.
Can you open the mimic model slide, please, again? the next one. So in here, let's say we are gonna predict if the person has diabetes or not. So our target label is just zeros and ones, right? And for input for X, let's say clinical laboratory tests. So the output of the deep learning model will be something like between 0 and 1. So it has
Yes.
diabetes or not. So how the model mimics that one. So because X doesn't change, how does the whole thing works? Can you explain it again?
Okay, so for that, I need a marker.
No marker, no explanation.
Okay, then I will try to do that.
That's fine.
Okay, so let's assume that the decision boundary between diabetes and non-diabetes is extremely complex. Excellent, thank you. All right, so now suppose, so this is your X, this is your Y, and X maybe doesn't matter. This is really like 1,000 features. And your deep learning model is so this is your original outcome variable. This is your output from the deep learning model. I mean, this is a dry example. So I've simplified things. So one thing to notice is that let's just assume that these are instances which are also closer to one another in the n-dimensional space. If you really think about it, the output is also, in some sense of the word, so with respect to, say, the true output, there is some error, right? But at the same time, if we suppose that this is the ground truth, this is a phenomenon which is much simpler as compared to this one. So for a decision tree, it is difficult to model this. But because it's simpler, a decision tree can model this. And the decision tree, of course, will have error associated with it also.
Any other question or comments?
While we have this slide, for example, when you use hybrid or mixed models together in serial, should we think about the concern the competition cost of the model?
So in this case,
the trial and errors.
okay, so in this case, the main competition cost is here. These other models, so the runtime is not very high. So okay, so if you can run this, then you can run this. Yes.
Well, when you do some trial and errors, then you try the same model with different parameters several times.
Okay. Now I get your question. So the same thing will apply over here. So your trial and error will be focused on this. And so once you get that, so it will give you that output, Y and N. So based on that, you can create n number of simpler models. So you don't have to like rerun this. You just take the output, save it somewhere, create a decision tree, SVM,
Regression model is necessary. The cost is not very high.
What the reference slide?
Oh, so like this is like a Bayes theorem.
Okay.
So this is actually like the foundations of. It is actually 1763. That's not a typo.
Any Any other comment or question? Okay, so on Monday, we're going to have the 5th tutorial at 5:30, and also on Monday we have a seminar, which is, the title is Machine Learning is Not Enough, You Need Expertise, and it's going to be at 12:15 at 129, room 129. Okay, so let's thank the speaker and see you all.